In this lecture, we are going to discuss some of the basics behind the principles of soil compaction, which is a very important function that geotechnical engineers are involved with. And this is kind of where the rubber meets the proverbial road. Compaction is performed on almost every site grading project, and it's a very necessary aspect to get the soil to perform adequately and to do the things that we want, to hold the loads that we want, the pavements that we want. And so whenever you see a big construction project going on, you're likely to see compaction going along with it. So I guess the fundamental underlying question we could ask is what are we trying to achieve by compacting the soil? So if you think about soil on a very micro scale, when we think of it in terms of solid particles and then void space, at the end of the day, what we're really trying to do is reduce the amount of the void space that's in the soil, because void space is bad for a lot of engineering purposes. So if we densify it and get the solid particles closer together, we can reduce the void space and we get more desirable behavior out of our soil. And why would we want a denser soil? Well, a few reasons. One, we might get a higher soil shear strength. So the tighter those soil particles are compacted together, the stronger the strength or the more load that they're able to bear. We generally get less settlement. Certain types of settlement comes or is amplified by the existence of voids in the soil. If we eliminate those voids or minimize them, then we get less settlement. Lower permeability. Now in some cases we may want permeability, but usually for load-bearing cases, we want to reduce the amount of permeability. We want the water to run off the top of the soil instead of run through and potentially erode our soil away. It also reduces the potential for seismic-induced soil liquefaction. We won't really talk about that in this class, more in my 545 class, the earthquake engineering class. But I just want you to be aware that that's one of the benefits of densifying soil. And finally, we're going to reduce the potential for the soil to rut and to wear and erode away. So these are all really desirable aspects of compacting soil, particularly prior to any mass grading project. So how do we establish a standard or I guess rules to define how we want to perform compaction? So the test that we use today is called a Proctor test or a standard Proctor test. Now the standard Proctor test, we're going to, let me erase some older notes there. We've got basically a container of a known volume, and that volume is 1/30th of a cubic foot. And so what we're going to do is we're going to put the soil into this container. But we're not going to just dump it in there in one specific lift. What we're going to do is we're going to use a hammer of a known mass, a 5.5 pound hammer that's going to be dropped over a distance of 12 inches. And we're going to put the soil into the mold in 3 different lifts. So for instance, we're going to come in here and we're going to put one lift down, fill it 1/3 of the way up, and then we're going to pound it with the hammer 25 times. And then we're going to come in and put another lift and pound that 25 times. And then we're going to come in and do the final lift and pound that 25 times. So all together we have 75 hammer blows that we're applying to this little mass of soil. Now the advantage of this, of course, is that when we do this, we know the volume of that mold. So we can get the density of the soil just by weighing it, because density is weight divided by volume. So here's what makes the Proctor test work. It's all based off a constant amount of energy. This is why it's important that we do the same number of hammer blows and that we drop the hammer the same distance for every single test. Now we can compute the amount of energy that goes into a standard Proctor test. It's our 5.5 pound hammer dropped 12 inches or 1 foot 25 times per layer, and there are 3 layers per test. So what this leads us to is almost 413 foot-pounds of energy applied to the soil per Proctor test. So what we're going to do is imagine that we have soil. We're going to put it into our mold. We're going to pound it with the hammer. That's my a futile attempt to draw a hammer pounding. And then when we're done, we're going to take the soil out and we're going to weigh it wet or moist, I guess is a better way to do it. Then we're going to put it in the oven, let it dry, and then we're going to weigh it dry. So essentially, when we weigh this whole this whole mold wet, what we are able to get is our total unit weight, or I guess to be consistent with our previous lectures, we'll call it our moist unit weight. And then once we get the dry unit weight, we're able to measure our moisture content. And then from that, we can compute our dry density given an assumed specific gravity. So then what we're going to do is we're going to plot dry density versus the moisture content in the mold. And so we get a single point. Then we're going to start all over, and we're going to add more moisture to the soil, and we're going to repeat the test, and we're going to get another point. Then we're going to start over again and add more moisture to the soil and repeat the test and get another point. What we're doing is we're creating a series of points of dry density of the soil in the mold versus the moisture content. Now, if we were to repeat this process over and over, for multiple points, and then we were to connect these points, what we'd get is a curve or a line that looks like this. And we call this curve or this line a compaction curve. And this compaction curve represents the densification behavior of the soil as a function of the moisture content that's in it. So what we see here in this initial portion of the curve increases, or the curve goes up, indicating that we get more dry density as we add moisture. Now, why in the world would that happen? Well, because adding water is going to lubricate the soil particles to a point and help them get closer and closer together when we add this 413 pounds or foot-pounds of energy. But it only works to a point, because if you think about it, if I have sand particles, sand particles, sand particles, where does the water reside in soil? Well, the water resides right in the void space. But ironically, it's the void space that we're trying to eliminate when we do compaction. So in essence, we're trying to add more water, but we're trying to minimize the space where that water will go. And eventually, we're going to reach an incompatible point where we're going to add water, but there's going to be nowhere for that water to go. And the only way we're going to get more water into that soil is the particles have to get farther apart so the void space can get bigger, so there's a place for the water to be. At that point, we're beginning to approach saturation of the soil, and we lose dry density because the soil particles are getting further apart, not closer together. That's what happens on this down side portion of this curve. Now there's a similar test to the standard Proctor test. We call it a modified Proctor test. Now the modified Proctor test uses the same mold and the same idea. We're going to put the soil into the mold in layers and we're going to compact it with a hammer. But here are some differences. We're going to use 5 layers instead of 3. We're still going to use 25 blows, not plows, blows per layer, but we're going to use a 10-pound hammer and we're going to drop it 1.5 feet or 18 inches instead of 12 inches. So if basically what we're doing is we're adding more energy to the soil. So in the standard Proctor test, we were adding about 413 foot-pounds of energy. Now, if I were to compute the amount of energy in the modified Proctor, 10 pounds in the hammer dropped over 1.5 feet, 25 times per layer, times 5 layers per test, we get 1,875 foot-pounds of energy per test. So roughly 4.5 times the energy as the standard Proctor test. So why in the world would we develop the same test but just put more energy into the soil? What are we trying to accomplish with this? Well, really what we're trying to accomplish is we want to simulate the compactive energy that modern compaction equipment uses today. Modern compaction equipment, heavy machinery, it's much more efficient and can deliver a lot more energy to the soil than older equipment. I mean, in the old days, they used to run herds of sheep back and forth across your site to compact the soil. Now today we use machinery to do this. So here's a question for you. We know then that we can apply different levels of energy to the Proctor test. And we know that each curve from a Proctor test is associated with a uniform or a constant amount of energy. So consider, for instance, these 3 curves. The lower curve, say that it's enough energy to be 90% of the standard Proctor. So what would that be? Roughly 370 foot-pounds of energy per test. And then this middle curve is the energy from a standard Proctor test, and this upper curve is the energy from a modified Proctor test. So ask yourself this question: what trend do I see with regard to maximum dry density, or the peak of the curve, and the optimum moisture content, or that's the moisture content relative or associated with the peak of that curve? Well, when we add more energy to the soil, as we'd expect, we're going to get a higher maximum dry density. That's because the greater amount of energy is going to get those soil particles closer and closer together. Now, as we add more energy to the soil, however, we're going to get a lower optimum moisture content. You can see that this peak is essentially moving up then and to the left as we increase energy. Now, one of the interesting things about these curves is that these curves tend to just kind of follow a path, and if we trace that path, we can call that path the line of optimums. We don't really use, or at least I'm not aware of using the line of optimums today for any design purpose, but it's just interesting to know that it's there. Now, I want to talk a little bit about this other line that you can see here. It's drawn roughly parallel to the line of optimums, and it's called the zero air voids curve, or the zero air voids line. Now, this line represents the absolute boundary of these compaction curves. It represents the point where all of the air has been pounded out of the soil and all that's left is water. So there's no more room for additional water to go unless we increase the void space and decrease the dry density. So we can calculate this line with just a very simple linear equation. So the equation of this line is given by this equation right here. But we want to modify it so that we're not using void ratio. And we're going to use our phase relationship equation that we introduced a few lectures ago. And because we know that the degree of saturation is 100%, that basically is going to go to 1. And then we can substitute specific gravity times moisture content for void ratio. And this is the equation then that we can use to plot our assumed zero air voids curve. We know a couple things, okay? All compaction curves must be to the left of the zero air voids curve. No compaction curves can cross it. And so it's really good practice to draw or plot this curve first and then plot your compaction curves. Now, if during testing you have any compaction curves that cross the zero air voids curve, then that's telling you that you either did your calculation wrong or your assumption regarding specific gravity is incorrect and it needs to be adjusted. So let's talk specifically about the structure of cohesive soil when we compact it. Now, cohesive soil is interesting because we have the double layers that we have to worry about. Now, when we're on the wet side of the compaction curve, so that's over here on the wet side, wet of optimum, there's so much water in the soil that essentially the double layers get really thick and the clay molecules get dispersed and spread. And so it contributes to dispersive type behavior. Now, if the soil particles become too aligned and becomes too dispersive, then the soil behaves really, really wet. And this can happen when in one of two ways. Either we add too much water or we add too much energy to the soil. And then the cohesive soil becomes like a viscous fluid and it shows pumping behavior. Here's a link to a video. You can't click on it just watching this, but I'll include the link down in the description box below to a machine operator who happened to just film some of his work where he showed the soil being pretty pumpy or jiggly as he calls it. It's a great example to show what soil looks like when it gets in this pumping or this dispersive condition. And in general, unless we're placing really deep fills, this is kind of an undesirable condition. We'd rather have the soil be dry of optimum, so the soil behaves more like a flocculated manner, because then the soil strength is generally better. The soil is usually more amenable to drainage, but it's harder for the contractor to hit compaction when the soil is dry of optimum. Now, I want to clarify or maybe give a little more examples of something I said earlier, that when you have when you can make a clay soil pump by one of two ways. You can either add too much water, and that one kind of makes sense, right? If we add too much water, then the soil is going to get soupy and it's going to behave in a viscous fluid kind of way. But the other one often throws a lot of people for a loop. It's add too much energy, or over-compacting the soil. And I'll show you how this works. So let me get my ruler out so I can draw some good axes to work with here. Okay, so now say I have a compaction curve. Looks something like this. This is moisture content. This is dry density on this axis. There we go. Now, for a given moisture content, say this value right here, you can see that I fall on the dry side of this compaction curve. I am less than the optimum moisture content. But the interesting thing is, like we discussed before, what happens if I increase the amount of energy applied to the soil? What's going to happen to this compaction curve? Well, the compaction curve goes up and to the left. So if that compaction curve goes up and to the left sufficiently, it might look like that, or even if I add more energy, it might look like that. I didn't change the moisture content, I just changed the amount of energy that's in there. Now if you look at the same moisture content we were at before, at this energy I'm close to optimum now. And at this higher energy I'm now on the wet side of the compaction curve, meaning that now the energy was sufficient to really get those soil particles closer together, and the amount of water I had before is now sufficient to fill the void space, and I'm approaching saturation. So by adding too much compaction or energy to fine-grained soils, we can get the soil to pump and act like this viscous fluid. So what are some of the effects of moisture content and compaction on soils? Well, let's look at this. So the effect on permeability. If I increase the moisture content, or if I go wet of optimum in the soil, this is going to lead to decreased soil permeability. So wet of optimum means that my soil is less permeable, less able to transmit water through it. So in general, we find it desirable that our moisture content in the soil after compaction should be between -1% and +3% of the optimum moisture content. And so in general, this is kind of like a guideline that we're giving to the contractor. Try to get that moisture content between -1% and +3% of the optimum moisture content. In terms of strength and stiffness, if we go wet in the soil and we go wet of optimum, that increased moisture content is going to lead to decreased shear strength and decreased soil stiffness. And that makes sense. It's going to behave more like a viscous fluid than it is a solid soil. And so we lose stiffness and strength. In terms of compressibility, and this is applicable specifically to cohesive soils, if we're at lower pressures, meaning if this is compaction in soils that are going to be shallow relative to the ground surface, then having a wet soil or being wet of optimum is going to give us more compression. However, interestingly enough, if we plan to have high pressures, in other words, the soil that we're compacting is going to be under lots of compacted fill. Lots of compacted fill will be on top of it. Then the wet of optimum will compress less, and dry of optimum is going to compress more. And in terms of shrink swell potential, being wet of optimum generally will decrease your potential for the soil to swell. It's already got a lot of water in it, and it's hard for more water to go in it and cause a problem. However, because it has a lot of water in it already, a soil that is wet of optimum has an increased shrink potential, because shrink occurs when you lose moisture. So here are a couple of just pictures and some very brief descriptions of some different types of compaction equipment. Everything from handheld compactors that get in tight spaces to sheep's foot rollers that are good for cohesive soil but not very good for cohesion-less soils. Smooth drum rollers, which are great for like finish passes and sands or sandy clays. Rubber tire rollers, which can apply a lot of pressure to a little area but don't have very good coverage, to vibratory drum rollers because they vibrate up and down. And so these are really good for granular or coarse-grained soils, but not so good for fine-grained soils. This vibratory action can actually over-compact fine-grained soils and lead to pumping. So let's get into the topic of evaluating compaction. So say you're an engineer out in the field. Your job is to observe the work of the contractor who's performing soil compaction and placing new fill at the site. So in general, how is this going to work? How does the contractor know that he or she is doing sufficient work or meeting the objectives? And in general, how does the field engineer, how can he or she measure that the contractor is doing a good job and meeting the specifications? Well, this is where a term called relative compaction comes into play. So in general, an engineer is going to write specifications or basically the rules of the game that the contractor needs to follow. And they're going to write it in terms of this relative compaction and a tolerable moisture or water content. So the relative compaction is generally a percentage of some stated Proctor test of dry density. And then the tolerable water content is some limit or bound within the optimum moisture content. So if we go back to, let me erase some of this here. If we go back and look at this plot here of this compaction curve, a relative compaction would be kind of like drawing a line on the dry density axis, where this might be, say, 95% of maximum dry density, where, of course, that point is the maximum dry density. Okay, and then the tolerable moisture content, think of that as boundaries on this axis. So really what we're telling the contractor is, look, you're compacting soil. You need to fall somewhere in this region right here, Mr. or Mrs. Contractor. If you do that, then we're good and you can keep placing more fill and we'll just keep going. If the contractor falls, say, meets the dry density specification but is too wet, it's bad. If the contractor meets this density specification but is too dry, then that's bad. If the moisture content specification is met but the dry density is not met, it's bad. And so in all of those cases, the soil would have to be ripped out and the contractor would have to redo it. So remember, a relative compaction is just a percent of some stated Proctor or maximum dry density from a Proctor test, either the standard or the modified Proctor test. Now, we've already talked about a term in an earlier lecture called relative density. And some students confuse relative compaction with relative density. Don't do that. Relative compaction is not the same as relative density. They're sort of related, but not really, because relative compaction is relative to some stated Proctor test. Relative density is relative to the maximum and the minimum void ratios of the soil. But if we were to develop a correlation, some researchers have done that and said, well, the relative compaction relative to a standard Proctor test is about correlated to relative density of the sand using this relationship here. Okay, so now you've got the rules set like we defined, and you're the field engineer, and your job is to make sure that the contractor's soil that he or she is placing will always fall within that allowable space. How are you going to do that? Well, one method that field engineers use is called a sand cone. So what we need to measure the dry density in the field, and we need to measure the moisture content in the field. So in the sand cone method, the engineer is going to go out with a shovel and they're going to dig a hole in the ground. And it's going to be some weird shape, of course. It's not going to be a perfect sphere or anything. They're just going to dig a hole in the ground. Then that soil that they dig out of that hole, they're going to weigh it. And then they're going to take the soil back and put it in an oven and weigh it again so they can get the dry weight. And that's where they're going to get the moisture content. But in order to get a dry density, we need the weight of the solids, which we got from the soil we dug out of the ground. But we also need a volume. How in the world are we going to get the volume of that hole that we dug in the ground? Well, one way we can do it is by filling the hole with a substance that has a very well-constrained and well-known unit weight or density. And so that would be like a material like Ottawa sand. We know the dry density of Ottawa sand with high level of confidence. And so if we take a bottle of Ottawa sand, and it usually has this little cone shape on the bottom of it so that the sand doesn't run all over the place and we can get it right in the hole that we dig. That's why they call it the sand cone. If we take this bottle and the cone and we weigh it before we put sand in the hole, so we get a total weight, and then we stick it over the hole we dug and we fill it with sand. So some sand is going to go down into the hole that we dug. After we fill the hole, we weigh our bottle and we weigh the cone again. And the difference of the amount of sand that we lost is going to be the amount of sand that went into the hole. And if we know the unit weight of that sand that went in the hole, we can compute the volume of the hole simply by taking the change in the weight. So that's going to be the change in the weight of the jar minus the weight of the sand that's in the cone, all divided by the unit weight of that sand, which we know. And that's how we're going to get the volume. So we can get a dry density that way from a sand cone. And the sand cone method is a very precise and reliable test. The only problem with it is that it takes a long time to do. You've got to dry your soil so you can get the weight of the solids. Now, most field engineers today use a different method. They're going to use a nuclear density gauge. The nuclear density gauge works because it has a radioactive source on the end of this rod that I'm highlighting right here. And that rod can get pushed down into the ground at different depths. And on the back end of the nuclear density gauge, inside of the gauge, there are a couple of sensors or detectors. And what they're sensing are gamma rays and fast neutrons that are being emitted by the radioactive source. Now, the density gauge is calibrated so that just by detecting how many gamma rays are reaching the sensor, we can correlate that to the dry density of the soil. And by measuring the amount of fast neutrons by the sensor, we can correlate that to the moisture content in the soil. And so basically this field engineer is going to go out, going to put this probe into the ground, going to push a button, wait about 8 seconds, and then right here on the screen, it's just going to tell the field engineer right away, your dry density is this, and your moisture content is this. And that's how it works. It's that simple. Now, to have authorization to use a nuclear density gauge is kind of a big deal because these radioactive sources on the end of these rods are quite radioactive. And so these devices are all governed and uh, I guess, managed and administered by the Nuclear Regulatory Commission. And so, in order to use these devices, you have to be field certified. You always have to get update certifications. You have to wear safety equipment badges that measure the amount of radiation that you're exposed to. And so, it's kind of a big deal. Not just anybody can use these devices in the field. So I often ask my students, which method is better? Is it better to use the nuclear density gauge, or is it better to use the CEEN code? And I always like to hear the different responses I get. Most students tend to lean towards the nuclear density gauge. I ask why, and the students say, well, because it's faster and it's more reliable. So I tell the students, well, it is faster. I'm going to give you that. But it's not necessarily more reliable. Nuclear density gauges can be very, very finicky, and they require constant calibration, at least every 6 months. If they go more than 6 months without being calibrated, they can give you some really wacky results. A sand cone method is much more reliable. If it's done right, and it's done by someone who doesn't cut corners, you can get really precise dry densities in the field and moisture contents. So, anyway, that's the end of the lecture. If you have any comments or questions, feel free to write a comment down below. I try to respond to those if I can. Or just shoot me an email and I'd be happy to respond to that as well. So I appreciate your time, and I hope you have a wonderful day, and I will look forward to seeing you in the next lecture.